Welcome everyone to lesson 2.5 from Precalculus, which is all about modeling with exponential functions, officially called exponential function context and data modeling. Let's get started. So some numerical representations of exponential functions don't necessarily look exponential. So remember that exponential means that it's increasing proportionally. We're multiplying consistently by the same number, either a number larger than 1 to increase or grow, and a number between 0 and 1 if we want it to decrease or decay. So if we start with a function like this, like f of x here, and we try to see if it's exponential, growing proportionally, we would check how many times larger is the next number. So here the next number is -1/2 times larger. This is 7 times larger, 19 sevenths, so on and so forth, not consistent. So it doesn't look or appear to be exponential. But if you did consecutive differences, you would also figure out that it's not linear, it's not quadratic, it's not cubic, it's not quartic. You're going to go on forever and you're not really going to get your pattern. So it is exponential, but how? Well, if we take f of x and we take every output value and we add 5 to it, we get this over here, which does convey an exponential pattern. This 3 to 6 to 12 to 24 to 48 is all multiplication by 2. So this function is 3 times 2 to the power of x. But since this function is 5 larger than f has to be 5 less. So we have that vertical shift down. How in the world do we tell? So you would actually use some skills from Algebra 1 to actually be able to do this. So the first thing you're going to do is you're going to take a data set like we have here, and you're going to find the difference between each of them. What do you need to add to get to the next one? So in this case, I needed to add 3, then I need to add 6, then I need to add 12, then I need to add 24. And I've taken this f function from up here to do it. All of those differences have a common ratio of 2. So that's what our b is. So our b is going to be 2. So we have a function in the form of f of x equals a times 2 to the power of x plus k. How do I figure out what a and k are? Well, I could take some points, plug them into x and f of x, and make a system of equations. So I took the points 0, -2, and 1, 1, plugged them into the function, and I got -2 equals a plus k, and 1 equals 2 times a plus k. I solved them both for k, and set them equal to each other. Solved that and got a equals 3. From this, I was able to get that k was -5, and I get the equation f of x equals 3 times 2 to the power of x minus 5. All analytically, all without having to do any weird stuff, like know that I needed to shift it up plus 5, because I really didn't know that. So let's do that together here. So we have an increase by 1 for all of our inputs, so we're good there. 6 to 12 is times 2, 12 to 36 is times 3. That's different. So the first thing we're going to do is we're actually going to figure out what's going on here. So this is plus 6. I know that pretty well. This is plus 24. I don't know that off the top of my head. So let's turn our calculator on, and let's do 132, take away 36, and we get 96. So this is plus 96. That one, oof. 516, take away 132, and I get, oh my, 384. Great. Is this proportional? Well, we can actually see that. We can do 24 divided by 6 that's 4. What's 96? What's 96 divided by 24? Is that also 4? That's good. What about 384 divided by 96? Ah, okay. So we get times 4 times 4. So that means our b is 4. So we have a function f of x is equal to a times 4 to the power of x plus k. Let's take some points. Let's take this 0, 6, and 1, 12. So 0, 6, 1, 12, and plug those in. So we get 6 is equal to a plus k, and then we get 12 is equal to 4a plus k. Now, you notice that both of these have a k, just a regular k, So if I solve these for k, I would get 6 minus a is equal to k, and 12 minus 4a is equal to k. So I can set those equal to each other. So 6 minus a is equal to k, and 12 minus 4a is equal to k. Perfect. So what that means for us is that 3a is equal to 6, or a is equal to 2. And if a is equal to 2, then k has to be 4, because 2 plus 4 is 6. So our function here is f of x is equal to 2 for our a times 4 to the power of x plus 4. Not too bad. What about regressions? We've talked about regressions before with polynomials, but now we're going to start to talk with them about exponentials. So how do we do that? Well, the same way we did before. So we're going to clear this out. We're going to go to statistics and enter so we can modify our list. If you have anything in your lists already, you can hit clear on the list, and that is perfectly fine. Don't delete, because I'll show you what happens. If I go to list 3 and I hit delete, list 3 goes away. And I don't know an easy way to get that back besides resetting the RAM, so don't delete, just clear. What we're going to do is we're going to put our x's in for list 1 and our y's in for list 2 like we did before. And then we can quit. So second mode quits us out. So now we want to check that our calculator is giving us all of our statistics information. So we're going to hit mode, and we want to go down, and we want stat diagnostics to be on. Once it's on, we're going to go to statistics, calculate, and we're going to find the exponential regression, which is 0 in this calculator. It might be different on yours, so make sure you check. Enter. X is list 1, Y is list 2, and what we're going to do, something a little bit different, is we're going to store our regression equation. So we want to store that in our y1 and our y equals screen. To do that, we need to go to variables, V-A-R-S, vars, and we're going to go to our y variables here, function, and y1. What this is going to do is when it calculates what this regression equation is, it's going to store it in the y1 of our y equals screen so we can do more with it later. And we don't have to worry about, did we round appropriately and all that jazz. So once we have all this, we're going to go down and we're going to hit calculate, and we're going to get all of this stuff. So we get y of x, because we have y and x here, is equal to a, which is 4.9395. That actually rounds up. So 4.94, my bad, times our b is 2.203, no, I messed up again. 2.203 to the power of x. So when we write ours out, that's all we really need to write in terms of if I ask you for an equation. But it's always nice to have more accurate data. So that's why we're storing it, because we have all these lovely decimals that we can keep, and we don't have to write them down, all that jazz. The r and r squared are the reason why we turn the stat diagnostics on. They tell us how good our model is. And we look at r squared. So what this tells me is that our model is 99% accurate. That's awesome. So our model is going to be a good predictor. So here we can quit. Oh. And if we want to figure out what year 7 is, we want to plug in 7 to our function. And we have two major ways of doing that. I have my preferred way, but there is a way of doing it. That is one time only. You can go to variables, y variables, and we pick that y1. And just like function notation, you can use it as function notation. y1 of 7, well, that is, so y of 7 is equal to 1245.727, so 1245.727. Awesome. There's another way to do it as well that if you're doing multiple evaluations, could save you some time. First thing we're going to do is we're going to go to table set, and we want our independent to be ask. We can go to the table, and then we can put in 7 for x, and we get that value for y. So perfect. Two ways to do it. Always nice to have more than one way. But if we want to figure out when the debt's going to be 5,000, we have to graph it. We don't have the tools in our repertoire to be able to solve these types of equations yet, and that's okay. So what we're going to do is we're actually going to make y2 5,000. And if I hit graph, what's going to happen is it's going to graph this in a 10 by 10 window. 5,000 doesn't show up in a 10 by 10 window. So we need to go to window, and we need to change our Y max to something more than 5,000, like 5,500. It doesn't matter as long as it's larger. We hit graph, we're going to see our beautiful exponential, and then 5,000. We want to see an intersection on our screen, and we do. Awesome. So we're going to go to second, calculate, and we want to find the intersection. So first curve, enter, second curve, enter, and the intersection is, the Y value is 5,000, makes sense, but the X value, which is X, is equal to 8.759. So if it asks in what year would the debt be 5,000, it would be in year 8, so on and so forth. You write the debt would be so on and so forth, right? That's it. That's how you use the calculator to help you out a lot with this kind of stuff. Again, any type of regression question, you're going to have a calculator. So it's good to know how to use your calculator and some tips and tricks on how to use it a little bit more effectively. So let's continue, and we're going to talk about what's called the natural number. So we're not really going to use it much right now, but it's huge, and its uses are numerous. So the natural number is also known as Euler's constant. So it's named after this really, really famous German mathematician that did so much in the realm of mathematics. And it's an interesting number that has a lot of interesting properties when it's the base of an exponential. And it is represented by this e, little e, and we can actually find out what that is by going right here. Second division gives us e, and we can see that it's about 2.718. It goes on forever like pi. It doesn't follow a pattern. It's irrational. So it's the second most used non-rational number, irrational number. It's called the natural number because it's useful for modeling growth that's uninhibited natural growth. So for example, if we stuck like 2 rabbits in a room, how many rabbits would we have in 3 years? We could use an Euler's constant, or we could use the natural number to help us out with that. If we had a bank account, a magic bank account that compounded interest continuously, second by second, millisecond by millisecond, Euler's constant would be used for that as well. That's it for the natural number right now. It really does make some beautiful exponential curves that have some really, really nice properties, and we'll talk more about that specifically in calculus. But I digress. Let's move on. So when we're modeling, we can model percent increases and decreases to a population or an amount of something, so on and so forth. If it continually grows by a percentage or continually decreases by a percentage each year or each increment, right? So if it's increasing by 5% every time you measure it, then it would be a 5% increase, decreasing by 5%, so on and so forth. So the base of our exponential is 1 plus or minus whatever that percent change is. It's plus if it's increasing, minus if it's decreasing, but it's all based off of the number 1, which makes sense. That's a threshold between exponential growth and exponential decay. So if we have a 5% increase, it's going to be a base of 1.05. 5% decrease would be a base of 0.95. Cool. So let's find the percent increases and decreases of these functions. So I already know that 1.2 is 1 plus 0.2, so this is an increase of 20%. Again, when you write that, it's nice to write it as a percentage. It puts it more in context. Here, pretty easy. 0.7 is equal to 1 minus 0.3, so that would be a 30% decrease. This one's a little bit harder to tell. It's definitely less than 1, so what we can do is actually do 1 minus this number, 0.025. So this means that 0.025 is equal to 1, take away 0.975, or we have a 97.5 decrease. Not bad at all. How can we revert that and take initial values and percent increases and decreases to make functions? Well, let's try that out here. Ohm's value starts here and grows by 1.5%, so that would be V of t is equal to 200,000 times 1 plus 1.5%, and that is it. Decrease, same kind of idea. So we have grass g of t is equal to 1800 times, that one I'm not quite sure of off the top of my head, so I'm going to do 1 take away 0.281, and I get 0.719 to the power of t. I want you to try these out, pause the video and try these out, but I'm going to start now. This one is going to be P of D is equal to 150 times 3.05 to the D power, and this one is going to be, I guess, F of T is equal to 11,000 times, that'd be 1 take away 15.7. Oh, no, it would be 1 take away 0.157. So it would be 0.843 to the power of t. So again, not bad at all. Two common models for exponentials are half-lives and double time, if you will. How long it takes for something radioactive to have half of the material left, and how long it takes for usually populations or money to double. So to do that, our base would be 1/2 for half-life, that makes sense. 2 for doubling, that makes sense. The weird part is we have now a rational power where the denominator of the power is the time needed to half or double, because we're not always measuring in that amount of time. Maybe x is in years and the half-life is 5 years, so it would be x over 5. Not too bad. So let's make some functions. You have 150 grams G of a radioactive material with a half-life of 4,400 years. So we have f of x is equal to, we started with 150. It is having half-life, and it's having every 4,400 years. So you have x divided by that. Because there's no way that we're going to make x equal to 4,400 years in that increment, because that's strange. Like, you wouldn't really do that kind of thing. So I have 30 pairs of cool socks, and I double my amount of socks every 4 years. So S of t is equal to 30 times 2 to the power of t divided by 4. Not bad at all. What this means, though, is if we can modify time frames, we can actually modify the units of our exponential functions. So if I have an exponential function that grows 5% per year, well, I can model that in months by raising the base to the power of 12 and then dividing the power by 12. Because those would cancel out because the power properties of exponents. But that would be how I'd represent it in months. Weeks, I would do 52. Days, I could do 365, and I can modify my exponentials to have different units by doing a unit conversion. And I think that's really cool. So that is it for this lesson. If you have any questions, make sure you ask me in class. Otherwise, I'll see you in the next video.